Today we're going to implement rich regression from scratch in Python. I already have two videos on this channel where I show you how to do linear regression from scratch in Python. In both videos there's a mathematical part and an implementation part. One is about gradient descent, one about the matrix notation of the closed form, so directly computing the optimal parameters. And today we're going to do a regularized version of linear regression from scratch in Python, again with a mathematical part and an implementation part. To be precise, rich regression. So the L2 norm here as the penalty term. This video is going to be quite mathematical, so if you like it, let me know by hitting the like button and subscribing. But now let us get right into it. Alright, so we're going to implement rich regression from scratch in Python today. And as I mentioned, we're going to start with a mathematical portion where I'm going to derive the entire formula from scratch, and then we're going to put this formula into code. So we're going to basically calculate without doing some approximation or optimization. We're not going to use gradient descent. We're going to use the closed form. We're going to directly calculate the optimal parameters, considering a penalty term, a regularization term, which is the L2 norm. So we're going to talk about this here in a second. Now, although I'm going to derive the entire thing from scratch here, I still recommend you watch the other videos first because you're going to need an understanding of linear regression in order to understand regularized linear regression. So I'm not going to explain the concept of linear regression here from scratch. I'm just going to focus on the addition of the regularization term. But nevertheless, I'm going to derive the entire mathematics, and I'm going to also write the code from scratch. So the basic idea is that we have the residual sum of squares given a set of parameters beta. And this is essentially in matrix notation y, the actual result, minus x times the parameters, so the input times the parameters or coefficients, and that transposed times itself, so basically the entire thing squared. This is just the residual sum of squares, nothing fancy here. This is the ordinary linear regression. Now, what we're doing with rich regression and also with lasso regression, but with a different penalty term, is we're adding something at the end of this to say we want to penalize large beta values. So we're going to say there is some factor that we want to use. Let's call it lambda. In the code, we're going to call it alpha later. So here now it's lambda, and in the code later on, it's going to be alpha for this parameter. We're going to take this and we're going to multiply it by the square of the parameters. So beta transposed beta. That is the basic idea. We're penalizing large values here. And the effect that this has is we're relying on fewer parameters, although it's not going to probably set them exactly to 0. This is something that lasso does. Rich is going to make certain coefficients very, very small, which means it makes certain dimensions of the input very irrelevant, and it focuses on a couple of key features, so to say, to make a prediction, thus regularizing our line. And now with this, what we can do is we can derive the optimal solution for this. So first of all, we can expand this. We can say this is basically y transposed y. Then we can say this is essentially just beta transposed x transposed y. And then we can say this is y transposed x beta. Then here we just have the squares. So beta transposed x beta. And then we still have what we had before, which is this lambda times beta transposed beta. That is now the expanded form of that. Now, with this in mind, we can think about this in terms of, this is just the loss itself. Now we want to take the derivative of the loss, because think about this, what we're trying to do is we're trying to find the optimal beta, so the optimal set of coefficients given this new regularization term. So we now have this regularization term here. This changes our optimal solution in a way, and in order to find the optimal solution, we need to take the partial derivative of this arrow function, and we need to say, okay, what is it with respect to beta? And then we want to set that to 0 to get an extreme value, which is going to be the minimum. So we want to minimize this residual sum of squares here. So what we're going to do is we're going to say the partial derivative of RSS with respect to beta. By the way, I'm not going to explain calculus or matrix notation here. I expect you to know this if you're interested in this mathematical part. Otherwise, by the way, feel free to skip forward to the coding part if that's what you're interested in. Here I'm just showing you how to implement this. But basically, we can say the derivative is, here we don't have a beta term, so that's 0, minus here we have xty. Then here we have ytx. By the way, we can, since this is one-dimensional, we can actually just combine this to 2xty. Then here now we have a square, so to say, so we need to take the exponent down. If you think about this in terms of ordinary derivatives, so we need to say 2 times, and then we still need to say xtx, but we only have one beta left. So xtx and beta, and then plus, and here we have the same idea, 2 times lambda beta. Now, since we have a bunch of 2's here, I can just say divide by 2, and we still have that this entire thing is 0 minus xty plus xtx plus lambda beta. And now the question is, we want to set this to 0, so we need to say 0 is equal to, and we're going to call this now beta hat, because that basically means that this is the optimal set of parameters. And by the way, I'm missing a beta here, so we also need to say beta hat here. And now we're trying to get this optimal beta. So we need to restructure this whole equation so that we get beta hat on one side. How can we do that? First of all, we can say that 0 is basically negating this right side. So we just take this and bring it to the other side, but we're going to keep the 0 on the left side here for simplicity. So it becomes x transposed y minus xtx beta hat minus lambda beta hat. And now we can just put this part here onto the other side. So we can say that actually xtx beta hat plus lambda beta hat is equal to x transposed y. And then we can now pull out the beta hat. We can say xtx plus lambda. Now this is the identity matrix because we don't have the beta here anymore, and this is a scalar. So we need to keep it in the matrix notation, and then that's going to be equal to that. Now we need to divide, so to say, but in the matrix world, we don't divide, so we actually multiply with the inverse. Since this is going to be positive, we're going to say the inverse exists, and then we say beta hat is equal to, and then we basically have to take this, the inverse of this, and then times xty. So that would be xtx plus lambda identity matrix to the power of -1 xty. And there you go. That is actually the mathematical part. This is rich. This is the rich regression. Now, one more thing that I want to show you here in terms of the difference between rich and lasso. If you use the L2 norm, you have a penalty gradient that looks like this. If you use the L1 norm, which is just the absolute value, not just square that we used. Remember, we used the square up here as a penalty. What was it here? B transpose or beta transpose beta. You can also just take the absolute value. That would be lasso regression. And you can just see that it's much more strict and more likely to end up on a specific axis, which means we're going to more likely just get to an absolute 0 value, eliminating entire factors or features. So having covered the mathematical side, let us now move on to the implementation. Let's take all of this and put it into code, or actually we're just going to put the final piece into code. And for this, I'm going to open up my terminal, navigate to my coding directory or tutorial directory here. And we're only going to need one external Python package for the implementation. It's not cheating. We're just using NumPy, so we don't have to do the matrix calculations manually. But besides that, we're not going to use anything. We're not going to use scikit-learn or TensorFlow or any other machine learning package for this. However, we are going to use scikit-learn for the evaluation part. So the implementation is going to be just NumPy and Core Python, but we're also going to install scikit-learn so that we can then compare it to the scikit-learn implementation in terms of performance. So what I'm going to do now is I'm going to create a new UV environment. If you don't want to use UV, you can just go and say pip or pip3 install and then numpy and scikit-learn. These are the two packages we're going to need. In my case, since I have UV, I'm going to say UV add instead. Both is fine. Choose the one that you like. And now I'm going to just open up the main py file here. I'm going to delete all the code. We're going to start from scratch. And we're going to now just say import numpy SNP, and we're going to create a class which I'm going to call rich regression. Actually, just rich regression. That's fine. And the first thing is we want to define the init method, so self. We also want to pass an alpha value. We're not going to use lambda because lambda is a reserved keyword in Python, and alpha is also what scikit-learn uses, so that's fine. We're going to start with a default of 1. And then we're going to say self.alpha is obviously going to be alpha. Above that, self.coefficients is going to be none, and self.intercept is going to be 0.0, and that's also learned. So we're going to add an underscore afterwards. These are just scikit-learn notations. You don't have to use them. I just like to have it in the same style of scikit-learn. Now the fit function is where all the magic happens. We're going to take self here, of course, and x and y as parameters. So this is the training data, so to say. And we're going to say x is equal to np array of x. So we're turning this into the NumPy world. We're converting this into the NumPy cosmos. And basically what we need to do now is we need to somehow add the bias term for the intercept. For the intercept, we need to consider that you have always 1 in terms of the coefficient, but you need a specific intercept. So we're going to kind of just concatenate it with the original x data. So basically xb, x with the bias, is going to be np concatenate. So c underscore, I'm going to say np ones, and the shape here is going to be x dot shape 0 and then 1, and that whole thing is going to be concatenated with x. So that is now with the bias. Then we need to create an identity matrix for our formula, because remember we have here this specific term here with the I. We need to somehow create this. For that I'm going to get the penalty dimensionality, which is going to be xb shape 1. And then I is going to be equal to npi with the penalty dimension. And then I'm going to say that we're not going to penalize the bias term. Because of that, I'm going to say 0, 0 is going to be 0, 0. So we're not going to have a 1 in this particular first place of the diagonal because we don't want to penalize the bias term. We only want to penalize the actual weights. And then basically the entire magic happens in a single line. Let's pull up our formula here to put it into Python code, because that's the only thing that actually happens here. We're going to say a is equal to, and now we're going to apply this. We're going to take xb dot t matrix multiplication with xb, because that's basically the square here, plus alpha times, and then we have the identity matrix I. This whole thing has to be inverted. So for that, we're going to use NumPy linear, come on, where's my dot? Linear algebra dot invert. So that is now the inverse matrix of that term. And then we're going to take that matrix multiplication with xb transposed, and then that whole thing multiplied by y. That is the whole magic. That is the only calculation step. Now we need to say that self.coefficients and self.intercept are going to be set based on that. So intercept is going to be a0, and coefficients is going to be a everything after that. And the prediction is the most trivial thing. We can say predict, we get self and some input. All we have to do here is we need to actually take the input, turn it into a NumPy array, so np array x, and then we're just going to return our input multiplied with self.coefficients plus self.intercept. So that is now our regularization here. And we can now basically test this by using a scikit-learn dataset and also by comparing it to the rich regression of scikit-learn. So I'm going to say from scikit-learn, sklearn datasets import fetch California housing. Would be easier if I had autocomplete. From sklearn dot linear models, or was it model or models? Let me just double check. Model, it was singular. Import, and it's not called rich regression, it's just called rich. And then from sklearn.metrics, we're going to import the R2 score, which is the R squared score. So what we can do now is we can say X and Y are equal to fetch California housing, return X, Y equals true. Then we can create an instance of our regression implementation, rich regression here with alpha. Let's set it to 2, just so we can see the effect of that when we compare it to scikit-learn. And I'm going to say reg fit x and y. We're not doing a train test split here, keeping it simple. If the score is roughly the same, it's correct. So y prediction is equal to our regression model predicting on x. And then the R2 score has to be printed. So R2 score will compare y prediction to y. Or actually, I think the best practice is to pass it the other way around. Y prediction. So now we can get out of here. We can say uv run main py. And that is going to say alpha is not defined because we need to use self.alpha. Obviously. So let's try this again. And we get a score. So now to compare this, we're going to just copy and paste this. We're going to go down here. We're going to do the same thing with just rich, which is from scikit-learn. And that should actually now, let's call this rec.sk. Run this again. And we can see we get the exact same score. We can also try to see what happens if we change this, let's say to 10, just so we can see if there's any difference at all. Run this, and we get a different score, and they also differ slightly. Now, it's not going to be the same. The reason for that is partly numerical, partly scikit-learn implementation, but it's basically the same score. And you can see both changed in the same way. So now this is how you implement rich regression from scratch in Python. And my exercise to you guys would be do the same thing with the lasso regression. So that's it for this video today. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services and a tutoring tab. There you can contact me if you need help with a project, with a startup, if you need some guidance, or if you just need one-on-one tutoring or something like that. You can contact me via email and LinkedIn at the bottom of the respective pages. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.